the special case when z is a function of x and y. We're in 3 space, and we have a surface. We have one equation, but it's an equation where z is a function of x and y. And we're going to grab a point on that surface. There's the equation of the surface. To go to parametric form, we need to have 2 parameters and describe every point on the surface. Z is a function of x and y, so x and y are natural choices for parameters. This is the default parametric form, or standard parametric form, or natural parametric form, where I use the coordinate variables as parameters. Now we'll just do the construction as before, but now the parameters are in the picture as well. X and y are my parameters, and I'm taking curves through the point on the surface. Now we just repeat the construction from last time. Push onto the surface. Take our 2 tangent vectors. Now we have a point and 2 vectors, and that gives us a tangent plane. Push onto the surface, push along one tangent vector, push along the other tangent vector. One thing to notice here is I'm using x and y for both objects because the x and y parameters are in the picture. So it lifts onto the surface, it lifts onto the tangent plane. This isn't always the best practice. Let's do an example to see. Z is a function of x and y. I do the default parameterization. Z is the function, xx, y is y, and my vector function in terms of x and y. Take my partial derivatives to get my tangent vectors. Y is treated as a constant, remember? Now x is treated as a constant. The notation for functions is the same as for the vectors. There's my partial derivative of the function with respect to x and with respect to y. My tangent plane now. At the point 2, 5. I push on to the plane, push onto the surface, and then I push along each tangent vector. Put in what the vectors are. Collect my vectors together. So this is in terms of the parameters S1 and S2. If I used X and Y, it's the same thing, right? They're just variables. You can call them what you want to call them. The confusion now comes going to parametric form from my vector form. For parametric form, I need to describe every point on the tangent plane. So it has an x, y, z coordinate, but I'm using x as a parameter and it's not the same x. It's confusing. There's my parametric form. I solve for the parameters in the first two equations and plug in the third. It doesn't always have to be the first two. Whichever two you can solve for, you plug in the third. It will always be the same equation. And there's the form of the tangent plane equation from the book. Parametric form and vector form. Let's do a schematic to put everything in one picture. We'll be using a schematic like this often. There's the point on the surface. We push to it. Take two curves going through that point with respect to the parameters from the surface. Take my tangent vectors. Now I've got a point and two vectors. That defines a plane. They're tangent vectors, so it's a tangent plane. To get the equation for the tangent plane, I need to push to any point on the plane. So I push onto the plane with the green, and then I push to the point with the blue. My tangent vectors, my partial derivatives with respect to the parameters of the surface. Then I need to scale those vectors to push to the point on the plane. I'll use S1 and S2 instead of X and Y. It's a new object, so you should use new parameters. So the push to the point, the green vector, a scale of one of the blue vectors, one of the slope vectors, and a scale of the other slope vector.